Look at a sprawling marketplace like this one in Kampala. Every day, our lives depend on a massive variety of physical materials that all seem to follow different rules. We rely on specific metals because of how they behave. We can hammer iron into thin roofing sheets because it's malleable, and we use aluminum for cooking pots because it transfers heat to our food. But right next to those metals, we find materials that behave in the opposite way. The carbon-based wood charcoal stacked in these tins isn't shiny or flexible. It's brittle enough to shatter, and it doesn't conduct heat or electricity. Why do materials occupying the same physical space exhibit such contradictory behaviors? Why does iron bend while carbon breaks? To understand why a pot conducts heat while charcoal burns, we have to look at the internal structure that organizes every element in our world, the periodic table. Early scientists like Mendeleev tried to organize elements by their atomic mass. But as this early table suggests, relying on weight alone led to gaps and errors in how they predicted an element's behavior. We know an element's identity is defined by a much more precise metric, its atomic number. This is simply the count of protons found in its nucleus. Orbiting that nucleus are the electrons. These electrons distribute into specific shells that have strict limits. The first shell can only hold 2, the second holds 8, and the third holds 8. We see this in a sodium atom. Sodium's atomic number is 11, meaning 11 protons in its center. To balance them, it has 11 electrons, 2 in the first shell, 8 in the second, and 1 final electron in the outermost shell. This isn't a random cloud of particles. It is a structured system where the number of electrons in the outermost shell, the valence electrons, determines how the element interacts with the world. Electron count translates to the periodic table's layout. Sodium's single outer electron puts it in group 1's vertical column. Its 3 shells place it in the third horizontal row, or period. A staircase line then separates the metals on the left from right-side nonmetals. Most elements are looking for one thing: stability. In chemistry, stability means having a completely full outer shell, like the unreactive noble gases. Left-side metals have few outer electrons. They achieve stability by shedding them entirely. Losing these negative electrons makes them positively charged ions. Right-side nonmetals are just a few electrons short of a full shell. They achieve stability by pulling electrons in, gaining a negative charge. This microscopic exchange, metals shedding electrons while nonmetals look to acquire them, is the reason materials have such drastically different physical properties. The periodic table acts as a map for these properties. By identifying an element's position on the grid, we can anticipate its behavior, knowing whether it will conduct heat or how it will react with other substances. Take aluminum. Its position on the left side tells us it's a metal, which is why it's a reliable choice for objects that need to be shaped or conduct electricity. On the other side is oxygen. As a group 6 nonmetal, it's a gas that is highly reactive, which is what allows it to support the burning of charcoal in a stove. We use aluminum for the pot and oxygen to feed the fire beneath it, because their atomic structures make them perfect for those specific jobs. From the air we breathe to the metal frames of our homes, the material world isn't random. It is an organized system following the predictable rules of the periodic table.